and then watch the online videos. Welcome back to ME 760 Engineering Analysis 1. So last time we talked about the line integrals, and we show how to do the line integral. Today let's finish this section of the book about the line integral and go to the second section, which will be about the surface integral. But before concluding this section, let's give an example about the line integral. So let's assume that we have an integral I that we want to perform, and this integral I is from A to B, and the integral, you knew that from last time, it is f dr, where f is a vector function, for example. So if function f is just 3x squared in the ith direction plus 2y z in the j direction plus y squared in the k direction. So as you know, delta r is just dx in the ith direction plus dy in the jth direction plus dz in the kth direction. So if you will substitute with f here and delta r here, you will end up with the integration I from A to B is just equal to 3x squared dx plus 2yz dy plus y squared dz. So this is, I just performed the dot product between f and delta r. So we should pause and ask our question, is I, the integral I, is path independent or not? Is it path independent or not? So last time we showed that for the integral to be path independent, the function f, the vector function f, should be what?
Equal to the gradient.
A gradient of a scalar function f, small or so. So if we can represent f as a gradient of a scalar function f, now we will see if this is the case, and in this case the integral will be path independent. So this is d by dx for f in the ith direction, and d by dy for f again in the jth direction, and this is d by dz for f in the kth direction. Okay, guys? So now, if we can prove, for example, that f1, what's f1? So f is just f1 in the ith direction plus f2 in the jth direction plus f3 in the kth direction. So we can just prove that this f1 is equal to df by dx in the x direction. So if you can represent f as equal to gradient, this means that f1 will be equal to df by dx. And now what's f1? 3x squared. So this is a must. We have to prove that this is a must. f1 equal to 3x squared, and let's see if we can form a function f, scalar function f, that the vector function f capital is the gradient of this scalar function. So this is what we try to do right now. What's f2? df by dy, and this is, as a must, should be equal to what? To yz. And what's f3? df by dz. And this is equal to what? Y squared. So if we call this equation equation number 1, equation number 2, equation number 3. And now, let's solve those equations. So let's integrate equation number 1. So let's integrate this equation. So df by dx equal to 3x squared. So what's f? 3 over 3 x cubed plus some constant function. Yes? So this constant function, I will call it g of y and z, because it does not depend on what? In x, but it depends on what? Y and z. And what's f? df by dy for this function? It's, if you integrate this function, is 0 plus what? dg by what? dg by dy. I'm integrating this function now with respect to what? With y. Okay, guys? And what's this equal from 2 to yz? So what's g? It will be y squared z, yes, plus some another function which is constant, yes, with respect to y is constant, yes. You are integrating with respect to what? Y. So h of z is constant with respect to y. Yes, guys? So now I can call this one number 5, and then again I will get to the last one. df by dz is equal to what? df by dz.
0 plus 0 plus dh.
So what is f? This is f. Yes? Yes, guys? So if you differentiate it with z, this term is what?
0.
Is 0, and you have to differentiate j with z. What's the differentiation of g with z? Is equal to what? Y squared plus dh dz. And what's df by dz from here? Y squared. So y squared plus dh by dz equal to y squared. So what's dh by dz? 0. Okay, guys? So what does mean dh by dz equal to 0? H is constant. Yes? So now I can call this number 6. H is equal to constant. So what will be the function now? F, x and y and z from 4, 5, and 6
X cubed plus
is equal to x cubed plus y squared z plus c. Yes, guys? So let's take the gradient of this function. What's the gradient? In the I direction plus in the j direction, yes, plus in the
y squared in the k.
huh?
Y squared in the k direction.
So this is equal to what? Look at f over there. Is it f? Yes, guys? So we proved that gradient of f equal to what? The f capital. So in this case, we search it for a gradient of a scalar function, yes, for this function f, and this is how we search it for the gradient. So we said, okay, if we have a function from the beginning, function f, that has component f1, f2, f3. In order to have this function equal to a gradient of another scalar function, I have to have f1 equal to df by dx, f2 equal to df by dy, f3 equal to df by dz. Then you will integrate the first one, you will get a function of what? Of x, and there is a constant of the other two variables, which is y and z. Yes? Then you use the second df by dy to differentiate it and get the second constant. Okay? Then you differentiate it again and get the third constant, and then have the final function differentiated to see if you will get it equal to f or not. Okay, guys? So what does it mean here? This? Huh? Yeah, so f, the integration of f dot dr on the contour C is equal to what? Which is a contour C like this from A to B will be equal to what? So it is path independent. Okay, guys? So last time we show theorem 1, and we said that for a line integral to be path independent, we have to have the function equal to what? Theorem 1, we said that for f dr from A to be path independent, f should be what? Gradient of f. Yes? Is there any other way to say that we have a path independent line integral? We have two more. So theorem 2 state that if we have f dr over a closed contour, so we'll make it like this. Closed contour is path independent if the integration of the function f dot dr over this closed contour is equal to 0. So this is theorem number 1. If we can represent the function as a gradient of a scalar function, the path integral is independent of the path. If we have a function f and we integrate this function f over a closed path from point A to point B, then we return it from C1, we return it to from C2. So we went from A to B this way and B to A this way. So it tells us that if this integration is equal to 0, this means that the integral from A to B is path independent. How to prove it? This is the proof. So this is the closed integral, meaning that I'm going from A to B, then from B to A. For this function f dot dr is just equal to going from A to B on path C1 for the function f dot dr plus going from what? Where? From B to A for f dot dr, but on what path? C2. So I can rewrite this equation as what? can rewrite this equation as from A to B f dot dr minus over what? C1. And this is from B to A, so I can flip the integration from A to what? B over what? C2 of f dot dr. So if this integral is equal to 0, what does it mean? From A to B of the f dot dr over C1 should be equal to what? So what does it mean? It means that if you have a function that you integrate, if you want to know if this will be a path independent or not, just integrate this function over a closed path, okay, and see if the integration over the closed path will give you 0 or not. So if the integration over the closed path will give you 0, this means that this function is what? The integration is what? Path independent. So there is a third theorem for the line integral, and this theorem states that if the function f is integrated over delta r on certain contour C, if it is path independent, then curl of f, which is curl of f, is equal to 0. And the reverse is true. So how to prove it? So if we have a function, and this function, the curl of this function is 0, this means that the integration of this function over dr is path independent. How to prove it? From theorem 1, if the integration is path independent, f should be equal to what? Gradient of what? Gradient of f. Yes, of a scalar. Okay, now, what's the curl of f? Curl of f is just curl of gradient of what? Of f. And what's the curl of a gradient? 0. Okay? So if you have a function, and this function, the curl of this function is equal to 0, the integration of this function over a path from point A to B, the integration will be path independent. And the reverse is true. The converse also true. And this is known, we will take it in this chapter, this is known as Stokes theorem. That if you have f dot dr equal to 0, the curl of f is equal to 0. Okay, guys. So now let's change gears and talk about the double integrals. So we talked about line integrals, and we showed that for a function, vector function f, to be path independent if it is integrated over certain path from point A to point B, we should have three things. First of all, if the function f, the vector function f, can be represented as a gradient of a scalar function f, so the integral is path independent integral. Second one is if we can prove that integrating this function, vector function f, over a closed loop or a closed path gives us 0, this means that this function also is what? If you integrate this function over a path, it will be path independent. And the third one is if this in a vector function f can have a 0, has a 0 curl. So if you take the curl of this function f and the curl is equal to 0, this means again that this function is what? If you integrate from point A to point B, will have a path independent. This is called conservative field force. Conservative field force. So whenever you have a path independent for a field of force, this means that this field of force is path independent. And this is very obvious again when we talked last time about what? The Earth is what? Gravitational field. And also in electromagnetic, what field is conservative field? The electromagnetic field. The electrostatic field is more specifically a path independent field. And you will notice that if you have any function or force F that's central force, what does mean central? It goes to a center, for example, and it goes like 1 over r or 1 over r squared or 1 over r cubed or whatever. All those functions are what? Goes to a center, and the force is inversely proportional to the center. Those types of forces will be called what? Conservative force. What is not a conservative force? What do you think? In nature. What's not a conservative force? Huh? Exactly, friction. So if you take your car and you go from point A to point B on, let's say, on a desert road, then you take this point A to point B in a skating board on an icy road. So it will be completely different. The work that you will do from here to here is much higher than from here to here if this rod is icy, for example, and this rod is just in unpaved road, because the friction forces goes like what? Some constant multiplied by the velocity, or velocity square, or whatever. So this function is non-conservative field. Non-conservative field. And this is usually friction. So, and again, you will notice that this function, when you try to integrate it, you will notice that it does not give you 0 in a closed contour like this. So if you go from here to here, and you will for example, spend some energy or work, do some work, and go back from here to here, it's completely different. I'll give you an example. For example, if you raise a pole like this, and you raise it from this point to this point, and then you put it in a top of a table, and then you put it here. Then in the table you have a jar which is filled with oil. Then you roll it and drop it here. So if you calculate the amount of energy that you take it from here to here, is just equal to what? The potential energy, mg multiplied by what? By h. And if you take the potential or the work that this pole did, you will notice that here the force is equal to what? Mg, which is the mass multiplied by what? By the acceleration, minus there is another force here, which is what? The pointing force, yes, which is a friction in this case, pointing force. And this force will be some constant multiplied by the velocity, and this is equal to what? M dv by dt. So now you have a differential equation to solve. If this is just this term is 0, you will end up with mgh like before, so they will cancel each other. But now, this is not mgh alone, this is mg minus kv, so you have the ball here will have more friction from the oil compared to the air, and you will notice that this term is not equal to this term. So this is non-conservative force. Did you understand, guys? So the third one is if the function can be represented as a curl, and this curl is equal to 0, this will give you a conservative field. So now let's talk about double integral. And before we go and describe the double integral for a vector function, we will just make a review for what you take in previous years in Calc 2 or Calc 3 for double integration. So usually for double integration, it's the usage of double integration is in, let's say, in volume under some surface. If you take Calc 1 or Calc 2, so you calculate the volume under the, let's say, under an area, surface area. So if this is x, this is y, this is z, and you have some surface area like this, and the projection of this surface area on the xy plane is just an area r, and this surface area here has f of x and y and z. It's a function f of x and y and z, let's say, or in this case, because it is just the area, so it will be f of x and y. So if you want to calculate the volume under this area, for example, all what you will do is you will choose a parallel pipe like this, and you integrate it. You integrated in this contour R here. So this will be what? This is the what? Delta x, and this is delta y. And what's the height here? F of x and what? F of x and y. So what's the volume delta V? Is delta x delta multiplied by what? F of x and y. So if you want to calculate the volume under the surface, this surface area, you have to integrate the function f of x and y over delta x delta y. Where is the integration limit? You will integrate in what area? So where is delta x delta y is located? Here. It's located here. Yes? So you will integrate over what? The region R. Yes, guys? You will integrate over the region R. Another application for the double integral is if you want to calculate certain area, for example. And if we are talking about a shape like this, and we have taken this as delta x delta y. So if we want to get the area will be what? You will integrate over R of what? Delta x delta y. This stuff is in the book, I think in chapter 7 or so, for the scalar integration, double integration and single integration and so on. So this is just the scalar if you are differentiating, integrating a scalar function. Another application, for example, that you took in calculus, if you want to calculate the mass in certain area R, and usually you will say the mass will be just the integration over the region R for um, um, a mass per unit area. So the units here is, let's say, kilogram per centimeter or meter square. And then you integrate over this area. R, you will get the total mass. This is one of the usage. Another usage for the double integral that you took in calculus is calculating the moment of inertia. I. And again, I for x square or y square is just equal to the integration for this x square or y square over dx dy over a region also R. So those are just some types of what? Of double integrals. So how we will evaluate the double integrals? How to evaluate double integral? Di is double integral. So let's assume that we have a contour like this in the xy. So same contour, xy, xy. So you can do the following. You can say, I will go from point A to B point A to point B through this contour h of x, and then go from B to A through g of x. Yes, guys? So all what you will do, you will say, okay, I will choose an element in the y direction. Then I will do what? I need you to concentrate here first in a second. You will say, I will choose an element like this. Then I will integrate this element from the contour g of x to the contour what? H of x. Then I will swipe this from A to B, and I will cover the whole area. Yes, guys? For your function. Or you can state that you will do it differently. How you will do it differently? You will choose to integrate from some function b of y here and another function q of y, and you will say, okay, I will integrate from the curve here or contour b of y to what? Q of y. Then I will swipe this element in what direction? In the y direction. So you will first integrate over what? Over x. Yes? And then you will integrate second over what? Over y. So we can write it like this. Double integration for a function f of x, y, and z will just be given by, you will integrate, we said that we will integrate first over what? Over y. So we'll be integrating over y. So it will be f of x, y will integrate over y, and y will go from what? G of x to what? G of x to h of x. Then once I integrate this, it will give me this what? This element here. I will integrate this element from where? A to B over what? Over x. Over x, from A to B over x. Yes, guys? And this is equal to what? This is exactly equal to what? This is exactly equal if I say I will go from b of y to what? Q of y for the function what? Fx and y, and then this will be over what? Over dx. Then I will integrate this from where to where? C to d over what? Over dy. So this is exactly the same. Do you have any question here? Guys, do you have any questions? Okay. So what if we want to do change of variable in our integration? Let's say y and x and y are function of parameter u, and I want to do change of variable. You also talk change of variable when you have your function x is a function of u and v, and function y is a function of u and v. So how to do the change of variable? The change of variable, if you are integrating over some region R for this f of x, y dx dy, will be, you will integrate now over the new region R star, because you are integrating over the new variables u and v. So you transform your region from R, which is a function of x and y, to a new region which is R star, which is a function of what? U and v. So in this case, this will be the same function. X is a function of u and v, and y is a function of u and v. And this is multiplied by the Jacobian. How many of you heard about the Jacobian before? du dv. This is the Jacobian. How many of you heard about the Jacobian before? I think almost all of you. So Jacobian J is equal to this, and it is just given by d of x and y by d of u and v, and it is just the determinant. I will write it here. So this is dx by du and dx by d what? By dv, and this is dy by du, and this is dy by dv. Okay, guys? To show an example, if we have polar coordinates, for example, and in polar coordinate, x is equal to r cosine theta, and y is equal to r sine theta. So u is r and v is theta. Jacobian will be just equal to what? Dx by du is dx by dr. What's dx by dr? And dx by the v, which is theta in this case, minus r sine theta, and the other one will be sine theta, r cosine theta. If you multiply, this will give you r cosine square theta, and this will be negative, it will be positive, r sine square theta. You will take r outside and to give you r multiplied by cosine square plus sine square is 1. So this will give you at the end what? R. So if we want to integrate a function of x and y over dx and dy over certain region R, and we want to transform it from Cartesian x and y to polar r and theta, So let's say if you are talking about some contour like this, and then you knew that, okay, x will go from here to here and y will go from here to here. Yes? When you do from r and theta, for example, so you will say r goes from r minimum here to r maximum here, and theta goes from this theta to this theta. Okay? So you will have different limits for the integration, and this will give you, it will be f of x is r cosine theta. You will change all the variable. X will be r cosine theta and y will be r sine theta, and dx dy will be removed by what? Jacobian multiplied by du dv. So the Jacobian is what? R, and du dv will be what? dr d theta. Okay, guys? So lastly, we will close this lecture by defining what we call connectivity. We'll define connectivity. So if you have a surface, and the surface is like this, you can define a contour. So this is the surface, and the surface is R, and you can define a contour C like this inside the surface. So the connectivity, it define a simply connected surface, for example. So we will say that for every symbol, sorry guys, for every symbol closed curve. So if you have a simple closed curve like this, in order to be simply connected, we can, so this is a contour here, C, for every symbol closed curve C. It can be shrunk to a point without leaving R. What do we mean? If we have a surface like this, and we have, how many contours we can draw in this surface? Infinitely many. If we can shrunk this contour to a point without this surface, without this contour leaving the surface, this is called simply connected surface. Of course, this is not true for lots of cases. It's assumed that we have our surfaces like this, but it has holes. It has holes like this. So the area of integration is everywhere except for inside those holes. Like in 3 dimension, if we have a torus. So the surface here, and it has a hole here. Okay, guys? So if we have a contour here, we can shrink the contour up to a point without leaving the surface. Yes? But if we have our contour here, what will happen if we shrink it? If we shrink this one, maybe the point will come here. Then we are outside of the what? Outside of the surface. So this is not a simply connected surface. Okay, guys? So simply connected is every symbol closed curve C can be shrunk to a point without leaving the R, contour R here. And if R contains holes, there are symbol closed curves that cannot be cannot be shrunk to a point without leaving R. So if we have the surface and this contour R, if it has n holes inside, so if R has n minus 1 holes, we call R to be n-fold connected. It's not simply connected anymore. Okay, guys? So I will stop here, and next time we will start the double integration for vector function, and we will talk about Green's theorem. Okay, guys? Do you have any question regarding today's lecture? So this is just a review. You will find this review, I think, in chapter 7 maybe of the book about the integrals. So just look at the chapter 7, read it, just skim through it, and you will get this information. Then we'll start next time about double integration for vector functions. Okay? Thank you.